Hello mates. In the previous videos we're doing examples of gravity. In this video we are just going to continue with the theory part of gravity, introducing new concepts. In the previous videos we're just doing the F using that formula F is equal to gmm over r squared. Now we're just going to introduce further concepts. The next concept is going to be gravity. Let's say gravity near the Earth's surface. That's the concept we are going to discuss now. Gravity near the Earth's surface. All right. Consider an object M1 at the Earth's surface, which means consider when we have the Earth like this. Imagine this is the Earth, right? This is our nice Africa like this, and Europe will be here, and we have our Madagascar and our Australia, and our South America will be there, and our America will be there, and like that. Consider that is our nice Earth, and consider an object here at the surface of Earth with a mass m1. Now, if you remember well, the objects that we've been considering in the previous examples, they were a bit further from the Earth's surface. They were maybe at this point, or when the moon was orbiting the Earth. Now we're considering an object at the surface of the Earth, like yourself. You're at the surface of the Earth, and you have a mass m1. The distance of separation is just re. When you measure, I don't think I mentioned this before in the previous videos. When you measure the distance, the r that you're going to put in the gravitational gravity formula, that r is measured from the center of the Earth. So here, when the object is at the surface of the Earth, the distance from the center of the Earth is just the radius of the Earth. It's just the radius of the Earth. So our r in our formula is just re, which is the radius of the Earth. So now let's calculate the force of gravity, or let's show how we are going to calculate the force of gravity. It's going to be gm, the mass of the Earth, and then m, the mass, this one, of this object, which is m1 over re squared. That's how we are going to calculate. That's how we're going to calculate the force of gravity on this object when it's at the surface of the Earth, because the re is equal to just the radius, as I mentioned before. But also we know that when something is at the what? Surface of the Earth, it has weight. So we can also calculate its weight. We know from F is equal to ma. We know that the weight will be equal to m, but this object has a mass m1, so it is mg, g being the acceleration due to gravity. But we know that this force, okay, the other thing that we know is these forces have to be the same. They have to be the same. The weight is due to gravity, and this is force due to gravity. So these two are basically the same. Weight is because of gravity. This is how we calculate the force of gravity. So it basically means these two are the same. So we can equate this to that. So therefore, my m1g is equal to g me m1 over re squared. That's what this basically means. And we can cancel out what can be cancelled out. Therefore, g is equal to gme over re squared. This is a very important formula, and sometimes you are asked to derive it. This is how you derive it. You put the object at the surface of the Earth, calculate the force due to gravity using universal law of gravitation, and then calculate using second law of motion by Newton. This is the second law of motion by Newton. So these are two. The first is the universal, and the second is Newton's second law. And you equate the two, because this weight is a force due to gravity, and this is actually a force due to gravity. So they have to be equal. You equate them like this, and then you come up with this gmm. This equation applies to other planets where me and re and g change to the respective planets and positions. Because what happens is, when you want to calculate, let's say, the g for the moon, you just put what? The mass of the moon and the radius of the moon. Then you calculate the g at the surface of the moon. If it's g at the surface of the sun, just put mass of the sun and radius of the sun. Then you calculate g. And also, you can use this to calculate g at any point outside the radius of the earth. Let's say your earth is here, but you actually want to calculate the g, the acceleration due to gravity, at that particular point. This point here, it's not at the surface anymore, but you have what? You have a radius. So it's just a matter of putting the radius here and the mass of the earth there. So this radius is no longer the radius of the earth, it's now the radius of this particular point here, of that particular point. So that's the radius that you'll be putting, and you get that particular g at that point. And you can see g decreases inversely with the square of the radius. With the square, as the radius goes up, g decreases it decreases inversely. With what? It's inversely proportional to the radius, to this radius. So that is what? That is that formula. Let's see an example. Example is saying estimate the effective g on the top of Mount Everest when it is 88 meters above sea level. So they are saying it's what? It's 8850 meters above sea level. That is the example. It's above sea level, 8850 above sea level. Okay, so g, we know that from this formula, g depends on the distance from the center of the earth. That's what we know. So there will be an effective value of g at what? At the top of Mount Everest, because let's say this is just sea level and then Mount Everest is like that. So this will be sea level. Let's just say, or this will be let me make it simpler. This will be sea level. Not way up there like that. Let's just say at the foot of the mountain, that is what? That is sea level. To make the diagram simpler. So if this is the sea level, and we are told that it's what? It's 8850 above sea level. 8850 meters above sea level. So now, g depends on the distance from what? From the center of the earth. The center of the earth is somewhere down there. It's somewhere down there because this is sea level, so it's somewhere down there. So here at the top of Mount Everest, there will be an effective value of g. I'm just going to call it g prime. It's an effective value of g. I want to distinguish from g, which is right at the surface of the earth or at sea level. This one will be g prime, which will be an effective that is at some particular point. So we can calculate that one. G prime will be equal to g mass of earth and then the r squared. R will be the distance of that point from the center of the earth, and as you can see, it will be the height of the mountain plus this radius, the normal radius of the earth. So it's going to be the 8850 plus the radius of the earth. So this will be equal to 6.67 times 10 to the power minus 11 for g. Mass of earth is 5.98 times 10 to the power of 24. All divided by, when you add up 8850 plus the radius of the earth, you get 6.389 times 10 to the power of 6 squared. That will be the answer when you add the radius of the earth plus 8850. Then it's just a matter of punching into your calculator. When you punch into your calculator correctly, you get that the effective acceleration due to gravity at the top of Mount Everest is 9.77 meters per second squared. That's basically the calculation for effective gravity. So this is just an estimate, because Earth is not a perfect sphere. It's just an estimate. We estimated that this to the center of the Earth is the radius of the Earth, but probably it's not exactly radius of the Earth, because the Earth is not a perfect sphere. So that was just an assumption that we used there. So yeah, you just need to take that into, not like take that into account, but you just need to know that Earth is not in a perfect sphere, but for our purposes, we're just going to assume that. So in the next video, we are going to talk about satellites. This was just a video to talk about gravity near the Earth's surface. In the next video, we are going to talk about satellites.